Should I turn this bad boy on?
Wait, are you ready?
Yep.
Okay, it's officially done. Okay, I'm Brandon. I'm going to be talking about topology today. In particular, I'm going to be talking about Dehn Twists and the mapping class group, which mapping class groups you can define for like any topological space, but today we're just going to be talking about surfaces. So to start, I just want to define, there's like some sort of basic terms. So what's a group, right? I feel like every time I give a talk here, I always start with what is a group. So if you just have some set S, and let's say you have some function which takes two elements of S and spits out some other element of S, you want a few things to hold. And I'm not going to write this function. Like I'm just going to write f of a, b just to be like a, b. It just makes everything nicer. So we want this operation to be associative, which means that ab times c is the same as multiplying bc times a. So this is not generally true. It seems sort of stupid because most of the operations we're familiar with, like addition, multiplication, are associative. But there's a bunch of weird operations you can have which are not necessarily associative. There has to be an identity element, so we'll call it E, such that if I multiply A by E on the right, or if I do EA, right, so now I'm multiplying by the identity on the left, then this is always going to be A. And the distinction between this left and right multiplication is important because in general this operation is not going to be commutative, right? So that's an important point. So in general, AB is not equal to BA. If it is, if AB equals BA, then the modern terminology is just commutative, but the word in group theory is abelian, which I think is named after like oval or something, but that doesn't matter. So this identity, this has to hold for all A in the set. And finally, for each element A, we want there to be some A inverse such that when I multiply A by A inverse on the left or the right, I just get the identity. So this notion of a group is a little bit abstract and sort of like, but it really does capture a lot of structures that we're already familiar with. So one example is if I take the set of integers and I have it, and I take my operation to be addition, then of course we know that a plus b plus c is the same as a plus b plus c. So this is okay. We know that the identity is 0 because a plus 0 equals 0 plus a. This is just a. And we know that the inverse is just negative a. So a minus a is just 0. And something we can talk about with elements of a group is the order of an element. So let's, just to sort of make it a little bit concrete, let's look at the space Z mod nz. Now, all this is, when we divide any integer by any other integer n, there is a set of remainders we can get. And these are going to be 0 through n minus 1. So the space Z mod nz is these sets of remainders up to this plus n equivalent. So the point here is that if I divide, or if I have like some 0 in here, then this is really like a class of elements. It's a set. So it's 0 plus every multiple of n. And what this is just saying is that if I'm dividing 11 by 4, right, I can get, what's 11 divided by 4? Right, this is like 2, or no, this is 2 times 4 plus 3. Right, so this remainder here is 3. But what about just 4 plus 7, right? It's going to give me the same thing. So we don't want to consider this 7. We sort of want to consider like this minimal thing. So this is just a set of remainders. And the way addition works in here is if I look at Z mod 4Z, right? So this is just going to be these classes 0, 1, 2, and 3. So it's sort of like clock arithmetic, where if I do 3 plus 2, right, I mean, we know this is 5, but in Z mod 4Z, this is just going to be 1, because we're taking the remainder of these things. And so what I want to define is the order of an element in some group, which I'm not going to call S, I'm going to call G. It's the smallest k, where k is just some positive integer, such that if so let's just denote the operation in G just with this dot. So if I do A times A times A, say k times, I want this to be the identity. So if we look at this Z mod 4Z, we see that the identity is still 0, just like in the usual integers. But unlike in the usual integers, if I just take any integer here and I start adding it to itself, it's just going to go to infinity, right, or negative infinity. So we see that none of the elements have finite order, right, but we'll never go back to 0. But in here, if I do 1 plus 1 plus 1 plus 1, this is 4. But what's the remainder of 4 when I divide by 4?
0.
0, exactly, right? So we say 1 has order 4. Similarly, 2 has order 2, because I can just do 2 plus 2 and I'll get 4 and then 0 again. Okay, so this is basically everything we're going to need to know about groups. And some other background. Now we're switching to topology. So, is everyone okay with groups, by the way? Okay, thumbs up. So, what's a topological space? So, I'm not actually going to give you the definition of a topological space because it's sort of unintuitive. It doesn't really make it clear why we care about the structure, but it's just some sort of just a collection of sets which satisfy some axioms and some underlying ambient space. Really, the reason we care about topological spaces is because they are the simplest types of spaces in math where we can make sense of continuous functions. When you think of continuous functions, you can just sort of use whatever intuition you have from like a calculus or just an algebra class, right? Like on the real line, the map which sends x to x squared is continuous, right? Like the graph just looks like this, and there's no kinks, there's no sort of holes or jumps or anywhere. Like everything is kosher, right? So the first thing we can do is put topology and algebra together, which, unsurprisingly, is called algebraic topology. And the most basic construction in algebraic topology is called the fundamental group. And before we get to the fundamental group, and really the only thing we care about is what homotopy is. Now, homotopy is just rigorously encapturing what our intuition tells us about continuous deformations. So, just the whole time, keep in mind that when I refer to topological spaces, just think of them as nice, these like bendy, whatever kind of easy spaces that we're used to. Because I'm not going to work with any nasty spaces today anyway. So I'm going to let F be a map between two topological spaces x and y, which is continuous. Well, F and G, they're anyway two maps. And I'm going to let I be the usual unit integral, which this is just a subset of the real line. Right, so this is nothing special. And I'm going to define a function h, which takes in two parameters, x and t. So t lives in the interval, and this point x is lives in this topological space x. And so this is going to be a homotopy between f and g if a few things hold. So we want h of x0 to be f of x. We want h of x1 to be g of x. And we want that, or I mean, sort of just by construction, each h of xt is continuous. Right? So sort of what this is looking like, so we can just look at how f and g sort of trace out paths in Y, right? Like if this is my topological space Y, and let's say F sort of looks like this, just as a function, and G sort of looks like this, then H is sort of, so this is F, this is G, and H is a map which continuously deforms F into G. And so it might help a little bit if I write H of xt to be this lowercase h. And so all this is really telling us is that this capital H, which for notational purposes I'm just writing with lowercase, is just a family of continuous maps. So it's sort of like, there's like a bunch of these things where I get a different continuous function for each value of t. And so this is sort of capturing our notion of continuous deformations. And so these maps between topological spaces x and y don't have to be just continuous. We can sort of put some, like a stronger condition on them, which is we want them to be homeomorphisms. So a function, a continuous function between x and y is a homeomorphism, or, well, I'm just assuming it's continuous, if it's bijective. And we want, right, so this is just saying it has a continuous inverse. So not all functions f even have an inverse from y to x, because if they're not bijective, then they won't have a well-defined two-sided inverse. And moreover, we want this inverse to be continuous. And so this is called a homeomorphism. And a result of this is that a homeomorphism between the two spaces x and y basically tell us that these spaces are the exact same. Like all of the topological properties we care about x are inherited by y, just by virtue of f being a homeomorphism. It's like a very strong condition. And so these homotopies, I said, they're all continuous functions. And so this deformation can be a little bit unintuitive. For example, there are a lot of spaces which you can homotope that you would not expect to be equivalent. For example, if I take the, let's say this is just a unit disk, right? So the closed unit disk, so it sort of contains the boundary, and it's filled in except at the origin, then I can homotope this to just a circle, right? And you're sort of doing this just by taking this puncture and you just spread it out. So intuitively, we want to think of homotopy as bending our space, but also shrinking and expanding it. So this sort of just gives you a nice picture of what's going on. But let's say we don't want to allow these sorts of stupid deformations, just because it can be a little bit difficult to work with sometimes. So an isotopy is it's just homotopy where each of these HTs, in addition to just as a result, F and G themselves are homeomorphisms. So this is, all it's really doing is saying that we have these two homeomorphisms, F and G, between the spaces x and y, and the way we're deforming them is that at each stage it's still a homeomorphism. And so you can homotope this punctured disk to the circle, but you can't isotope them, right? So that's the sort of the main point here.
Can you give a non-trivial example of an isotopy?
Non-trivial. Well, I guess you can construct a lot of non-trivial examples of isotopies, because if you have some topological space S, and let's say you have like some subspace, let's say like S prime, you can consider just homotopies in S prime. You can, I think the only condition you need is like compactness or something like of S. You can always extend them to ambient isotopies of S. So this is maybe beating around the bush a little bit, because I just gave you infinitely many isotopies without actually telling you what any of them are. It's just an existence result. I didn't actually write it down. I guess I did not come prepared with an example. I sort of just want to move on to what I'm going to talk about. But, sorry, if anybody knows any concrete isotopies, feel free to just shout them out at any point.
For knots, you just have like an isotopy of like a knot, for example, like just have like a normal circle in 3 space, and then just like have a version of that knot but twisted or like flowing through itself, but in a way that can like be recovered.
Oh yeah, sure.
That's like where isotopies pop up a lot. And
Yeah.
just 2 manifolds in general.
Yeah, that's a good example. Because the geometric intuition behind isotopies is that with homotopies we're allowed to bend, shrink, and expand, but with isotopies we're just allowed to bend. So I have never looked at a knot in my life. So thank you. Because I would not have come up with that. But okay, let's get into the.
Maybe would you say it's isotopy homotopy by homeomorphisms onto their image?
Yeah, sure.
Yeah, that's the weird thing. I'm pretty sure it's usually like homeomorphism onto the image. If you say it's just a homeomorphism, then like the image would have to be the entire space.
Yeah, I'm just trying to bury some details.
Oh, okay.
Yeah, I don't want to be like too technical.
Okay.
I mean, just assume everything's subjective, whatever, right? It doesn't matter. So, and then just some notation I'm going to fix is, so by SG, I'm going to mean a surface with G holes. So it's a surface. A sphere is a surface, right? If you know what these words mean, surfaces are just 2 manifolds. This means that they're objects, they're like these 3-dimensional objects which locally look like the Euclidean plane. So we live on Earth, right? And to us, everything looks very flat, but we know that the Earth is not flat. I hope everybody knows the Earth is not flat. We're all globe heads, right? So the reason everything looks flat is because we're only looking at the Earth locally. But like when you zoom out, you see it's actually like this curved surface. So the sphere is not the only example of that. Donuts are great examples, right? Formally, this is called a torus. This is not a torus. Or we can have as many holes as we want, right? And so when I have G holes, I'm just going to call it SG. We can also distinguish between holes and just punctures. So a hole is like if you're punching through the sphere, right? It's going to leave a hole, right? But if you take like a needle and you just kind of, then it's not going to be like a big hole, it's going to be a puncture. So this is not the same as a hole, and when there are G holes and N punctures, I'm going to write SGN. But that won't come up too much, because punctured surfaces are a little bit more delicate, well, a lot more delicate. But okay, now that we have this background, I can actually talk about what I want to talk about today. But before I move on, does anybody have any questions about like any of this algebra topology that I've introduced? And please ask questions, because chances are someone else has the same question and won't be asking it.
Do we need to like say what the fundamental group is, or is that going to be important?
Oh yeah, I guess I mentioned that. Sure, okay. So if you take a topological space X, right, and let's say I just fix a point in here, X naught, and I look at the image of a circle in X. So this is going to be some closed loop. It doesn't need to be this nice. It can be, let's just say it's all wiggly, right? Then we want to see which loops based at X naught in X we can homotope to other loops. So if we can homotope, let's say like F and G, right, where F and G are 2 images of the circle in my topological space X, then we're going to say they belong to the same homotopy class, right? And so this homotopy class defines an element of the fundamental group, which is just pi1 of X and X naught. And so what is pi1? It's the space of all homotopy classes. And some examples, if I just look at the filled-in disk, right? So this is including the origin. And I just fix a point, let's say just some X naught, and I take any loop, right? If I take any other loop, just visually you can see that I can pretty continuously contract it to this loop, right? Moreover, I can actually shrink all of these loops to a single point. And so this space has a trivial fundamental group, right? Which means that there are which means that there really are no distinct homotopy classes. But what if I take this disk with the puncture missing, right? Now, if I take any point which is not the puncture, say something here, and I take a loop around here, now you see if I try to shrink it all the way down to x naught, it's not possible. Because like I can get closer and closer, but once I'm like right next to this puncture, I can't actually go through it. And so now we have a non-trivial element of our fundamental group. And as it turns out, the fundamental group of the punctured disk is just the integers. Fundamental groups can be very, very complicated, and calculating them can be really hard. But these are just some basic examples. You can also tell, or you can figure out eventually that the fundamental group of the circle is also the integers. And one way of constructing the torus is that you see it's a circle this way, right? And you also see it's a circle this way. So the torus is really just the product of S1 of itself. And there's a result which just says that the fundamental group of this product is the product of the fundamental groups. So then we see that pi 1 of this torus is just Z2, or just Z cross Z, right? So these are just some basic calculations. But okay, now we can actually define what the mapping class group is, which is great because it's not very, this lends itself to a lot of pictures, which I hope people are okay with my artistic skill so far. These are like the most pictures I've drawn in like a long time. So okay.
Do you have a question?
Oh yeah, sure.
What do you mean by a set cross a set? What does that mean?
Oh, it's I should have been using this chart this whole time. So this is like pairs x, y, such that x is in S1 and y is in S1. Right, it's just a Cartesian product.
Okay.
Is it cool? So like, if you just look at the plane, right? So so the plane R2, right? This is really just R cross R. Because I can take any point this way, it's going to be an element of R. I can take any point this way, it's going to be an element of R.
So you're just creating like every permutation of every element in it.
Well, I wouldn't say permutation.
I mean, that's what you're...
Here.
Yeah, like all possible pairs.
Yeah.
Yeah, so that's it. So all possible pairs of elements in the circle are just give you this torus.
Ordered pairs specifically.
Sure. Yeah. Yeah. Okay. So what is the mapping class group? So mapping class group is like generally really important. So I'm going to call it mod S, or sorry, S is going to be a surface from here on out. So we can just take one of those to be our geometric picture in mind. So it's mod S, and this is, what's it called? This is really just the group of isotopy classes of orientation preserving homeomorphisms. Oh, sorry. So orientation is really just, like on these surfaces we have a well-defined notion of up and down, and we want our homeomorphisms to preserve this notion of up and down instead of like flipping it, for example. And the isotopies we're looking at are specifically the space of homeomorphisms which preserve orientation. So we're looking at isotopies between functions. And this is a group of the operation is just composition. It's a group, right? And so this is, all it is just, you want to look at functions which sort of map the space to itself in the same ways, right? This is intuitively what's going on. The only thing is that if S has punctures, then you want, then you want the homeomorphisms of the surface to leave the punctures invariant as a set. So they don't need to map punctures to punctures, but they need to map, or they don't need to map a puncture to itself, but it needs to map one puncture to another puncture. And this way you don't screw up any topological data. And the isotopies also have to leave the sets of punctures invariant. And then you can just define the mapping class group in the exact same way. So one example of this, and so what you also should note is that elements of the mapping class group are not single functions. It's an isotopy class of functions. So each element represents a whole set of functions. So if I draw my surface with 5 holes, or, yeah, that's 5, right? And let's pretend that the shape is symmetrical, even though we know it's not. So if I just kind of rotate it, right, I'm going to send this hole to this hole, and then in turn this one gets sent here, whatever. So this F, which this is in the mapping class group of S5, right? This is an order 5 element of the mapping class group. And we know it's order 5 because if I just rotate this thing 5 times, I'm going to get the identity, right? There are other mapping, and elements of the mapping class group are called mapping classes. So there are other mapping classes. One of them is really, really important and draws its name not from topology, but from number theory and geometry. But it's realized in it's really the same thing that's going on in that case, which is if I instead draw my surface to be like this long horizontal border, right? And let's say I sort of embed this into 3 space. So let's say I'm like holding like a really long donut, right? And so there's this sort of like this axis. There's this sort of axis this way, right? So if I rotate it along this axis by 180 degrees, then I'm just going to get the same thing just flipped upside down. This is an order 2 element in the mapping class group, and it's called a hyperelliptic involution. If you've seen this term in the setting of like elliptic curves, or just like more generally in arithmetic geometry, this is actually the same hyperelliptic involution. It's just realized topologically as a mapping class now, and that's really cool. And the hyperelliptic involution is a very special element of the mapping class group. We know it acts trivially on homology, but I'm not going to talk about that. We don't need to worry about these things. More generally, if I want to look at these rotations, let's say I just have some SG. There's a way that if I have a let's just do it for S2, right? If I take a 10-sided polygon, which, okay, 1, 2, okay. If I have S1, I take 1, 2, 3, 4, 5, 6. So this is going to be a 4G plus 2-sided regular polygon. I can always recover SG by folding the opposite sides. So I'm going to identify these 2 sides, these 2 sides, and these 2 sides. And when I fold these things up, you'll see I'll get a torus. This also works with just 4G-sided polygons, but when you add the +2, you get extra symmetry. And so we can get elements of the mapping class just by rotating it by like 1 click, right? I'm just going to send this side to this side. And this gives us like many non-trivial elements of the mapping class, group, because I can also send it here, and I can send it here. And the hyperelliptic involution is just realized by rotating it by 2G plus 1 clicks. So it's just 180 degree rotation. And so, what should we do now that I've given you a definition of it? Yeah.
But sorry, could you explain like what's the relation between the hexagon and the S1 thing? Yeah.
Okay.
Sorry.
If I take a hexagon, or let's just picture a square first, right? If I take a square and I fold up like opposite sides, what happens when I identify these 2 sides? What do I get?
Yeah, like cylinder.
Exactly, I get a cylinder, right? Now, okay, I have a cylinder, right? What happens when I identify the 2 bases of the cylinder?
Oh.
You get a torus, right? So as it turns out, you can also do this with a hexagon, you get the same thing. But as soon as you move to 8 sides, now you get a genus 2 thing, right? And if you go to 10 sides, then you still get genus 2. And notice that you always need an even number of sides because you're identifying opposite sides. So you can't just have like 1 extra side. So yeah, so this is, and like studying these regular polygons leads to something called translation services, which are super complicated and hard. But that's another talk another time. So let's actually try to compute some mapping class groups, because what's the point of defining it and not knowing what it is for anything? So there's something
I have a
called,
question.
yep.
So that first one for the torus, is that in order 6?
You mean this going this way?
Yeah.
Yeah. Yeah, so the thing about this is that you can like define these elements easily, but you can't really picture them easily, right? Because like, I have no idea how you would actually draw this element like if you just embedded the torus into R3 and tried to draw it, right? I don't really know what it looks like, but I can tell you that, mapping class group of the torus has to have an order 6 element. Actually, I'll get back to that later. Okay, so there's something called the Alexander trick, which is going to tell us a few things. So what I'm going to tell you is that the mapping class group of the closed disk, D2, is trivial. Right, okay. So let's prove this. Right, this is actually not that hard. So let's embed D2 to be in R2, right? So instead of looking at D2 abstractly, we can actually just picture a disk in the plane. And let's let phi be a homeomorphism from D2 to itself, such that phi restricted to the boundary of D2 is just the identity on the boundary, right? And then we're going to define f of xt, and you can already maybe guess what this is going to be, right? If I'm telling you that the mapping class group is a set of isotopy classes of functions, and I'm telling you that it's trivial, then this is, you can just guess, this is going to be an isotopy between phi and the identity, right? So all this is telling me is that if I have some non-trivial homeomorphism phi, which restricts to the identity on the boundary, then I'm always going to be able to isotope it to the identity function, which means that it's trivial, right? Because the identity is a trivial element of the mapping class group. So how am I going to define this thing? So I'm going to let it be 1 minus t times phi of x over 1 minus t. So this is really this function sort of changes with t. We're just telling it, this should be, yes. And then it's just going to be identity outside of that. Okay, I just wrote something down, but like sort of why does this work? Basically what's happening here is we're taking the disk, right? We're starting with the full disk, and at each t, what we're doing is we're applying phi to the disk of radius 1 minus t, and we're applying identity everywhere else. Now the only thing is that at t equals 1, you see this sort of breaks down. Or that's why this should be strict. And then f of x1 is just going to be the identity. And you can check that this is actually an isotopy of phi to the identity function. And the only thing is that these isotopies are still like continuous maps. And because we're in R2, we're in like the space where we can actually do calculus. And so we can think of smooth maps from D2 to itself. The problem with the Alexander trick, if we want to construct smooth isotopies instead of just continuous ones, is that it almost never works. Constructing something smooth like this in dimension 2 is extremely hard. There are infinitely dimensions where it's not possible to construct a smooth version. And the dimensions where a smooth construction has been found has always been like, extremely convoluted and really, really hard. So for us, just continuous is good enough. So a corollary is this, that we know there are a few other mapping class groups which are immediately trivial. And these are really just mapping, and these are just some other services which we can somehow relate to the closed disk in some way. And so we know that, so the first of these is if you take this closed disk and you remove any point, you also know that this mapping class group is trivial. And I'm just going to abbreviate it MCG. Now, this is just sort of immediate, right? Because now we don't even need to worry about what happens at 1. Because at 1, everything is like already shrunk down to a point. So this is just good enough. Like this is already isotopy. We're just defining this to deal with the origin. So that's the first corollary. The second one is that if we identify the sphere minus a point with the plane, and you can think of this, if I have a sphere, I just take a point out, now I can flatten it down to like a true plane. Then this gives you that the mapping class group of this punctured sphere is also trivial, and this is just by straight line homotopy, just because the plane and this closed disk, or the plane and the disk both have these straight line homotopies that we can do. So it's just the same thing. All the details are basically the same. And there's one more, which is the mapping class group of the two-sphere. And the reason we can do this is, like the actual sphere, the reason we can do this is that you can modify any homeomorphism of the sphere to fix a point, and then you just use this. Right? Because now you can isotope all of these homeomorphisms fixing a point to just trivial mapping classes. Or you can just isotope them to the identity. So you get a bunch of trivial stuff right away. But there's something which is non-trivial. The first example, which the details take quite a bit of work, but I'm just going to sort of sketch it. So it's for the annulus. Now, the annulus, in the plane, you can sort of think of it as just a circle here with a little circle cut out in the middle. You can sort of think of it as a cylinder. But the point is that the mapping class group of the annulus is actually the group of integers, right? So that's cool. And I'm just going to denote the annulus by A. Now, this sort of uses the theory of universal covers, which I will just illustrate for you. I'm not actually going to tell you what universal cover is. So universal cover, if I have some topological space down here, let's say this is a circle, then I want something that sort of lies above it in a sense, that literally covers this thing. And I also want it to be simply connected, which means that it has a trivial fundamental group. So in this case, the universal cover for the circle is just the real line. Now sort of, I'll draw arrows so you know it's infinite. Sort of how does this work? If I just take this point here and I just let it go to 0 up here, then every time I have some integer translation, let's say 1, or let's say I'm 2 over here, then the 0, 1, I'm just going to wrap around the circle. And then if I have 0 to 2, then I can just wrap it around twice. And in this way, you can sort of take the real line and wrap it around the circle infinitely many times. And this sort of gives you like a desired cover. Universal covers for surfaces are pretty easy. For the annulus, which the annulus just sort of is like this. The annulus really you can look at as just being like a cylinder. Then the universal cover is going to be R cross B interval, just because you have like the interval down here, and then it's just R is just going to be covering the space. If you have a surface with more than two or more poles, the universal cover is going to be the upper half plane. Which, when I say that, I mean like if I take the plane and I consider strictly the upper part, not including this axis or this x-axis, then the universal cover is just going to be this upper half plane, which sort of requires like some reruns. It's a little bit more advanced math, but you can show this is true. And for the torus, the universal cover is just the plane, right? Just the regular plane. So you just want to think of it as like some nice cover, where the reason we want it is because we can sort of do stuff down here, say in the circle, and we can lift it to what it means in the, we can lift it to something in the universal cover, do some stuff down here, come back down, and then get some desired results about the space down here, the base. Now, we're going to sort of, let's just let F be in the mapping class group, and let's say that, so remember, F is an equivalence class of functions, and let's say phi be some representative of F, or let's say, so all this means is that phi is an orientation-preserving homomorphism from the annulus to itself. And you can lift, so the universal cover of A, or the annulus, I'm just going to denote by this A tilde. So you can lift phi to the homeomorphism of the universal cover to itself. And we already know the universal cover of the annulus is just R across the interval. So we can just, so you can just think about that. I just don't want to write R cross I again, like every single time. And there's sort of this preferred lift, which says that this one fixes the origin, right? Because there are many different lifts in general, but we're just fixing one. And moreover, we can sort of set this phi1 to be, so this is this universal cover restricted to R cross 1. But this R cross 1, this is just the same as R. So what you see is that this phi1 is really a map from R to itself, right? And so because it's a lift of something which is the identity on the boundary of the annulus, then by some details that I'm mentioning, it has to be an integer translation on R, which just means that it has to take the form x mapped to some x plus n, where n is an integer. And so we can sort of define, and it's uniquely determined by where it maps 0, right? Because if it has the form x maps to x plus n, then 0 is just going to map to n, and now we have uniquely determined this phi1 tilde. And so, because the integer translations of R, it's just the integers, right? Like these are all the possible translations, then we can just sort of construct this map rho, which takes in this f, and this is just going to equal phi tilde 1 of 0. And this is going to be an integer. Right, so what we've done is we've taken a mapping class, we took some representative of the equivalence class of f phi, we lifted it to the universal cover phi tilde, we restricted it to R cross 1, which is just homeomorphic to R. Because it's a lift, and after that a restriction of this function phi, which has to be the identity on the annulus, or on the boundary of the annulus, then we know it has to be an integer translation. And we know that if I just plug in 0, right, then this phi1 tilde is determined by n. And so this function just tells you, this function rho, right, this is really what we care about here. This is taking in this f, and it's tracing all throughout this construction, and it's spitting out phi1 tilde of 0, right? So this is just going to be n. And so we know it's going to be an integer. Now, the real work here is showing, right? So this rho, what we've constructed is a map from the mapping class group to the integers. What we want to show is that this isn't actually, this is a bijection. By construction, you can see it's a homomorphism, which is a special type of map. So it respects whatever functions in the mapping class group, it maps to things, just respects the operation of the two groups. So we need to show that this map is injective and that it's surjective. So surjectivity is actually not that hard. So I'm going to actually skip the details for this one. But, I mean, I really don't want to, but I'm sort of running short on time. Really short on time, actually. But the idea for surjectivity, at least, which we're going to see pop up later, is that we know that linear transformations of the plane, these are given by some matrix which looks like this. And moreover, this preserves R across the interval. And so what this is telling us, just because it's in fancy language equivariant with respect to the group of depth transformations, this is going to descend. So this is really a map on R2, but it descends to a map on R across the interval. And thus it's going to be thus it's going to descend to a homeomorphism of the annulus. And so let's say eventually, right, this is just going to descend to some homeomorphism of the annulus to itself. And so now you can sort of define rho of this mapping class rho of the class of phi just to be n, right? Because we started with this n by construction. And so in this way, we get every single integer from some mapping class. And so this shows surjectivity. The reason I bring up this one in particular is because if I let n equals -1, then I can tell you, right, this is the annulus. And let's say this is just a line in the annulus. I can tell you exactly what the picture is. Because we want to see, like, what does this homeomorphism actually do? It's going to look like this. So this is going to be the image. This is an example of a Dehn twist. And which I do kind of want to get to. But I really want to get to. Finally, I'm definitely not going to go through the proof. I really wanted to, and then I was reading through the details of the mapping class group of the torus, which is, it's really nice. It's a nice argument, but you need to know some things about homology to understand it. So the mapping class of the torus, this is just SL2Z. SL2Z is just the group of determinant 1 matrices with entries in the integers. And the fact that and this is actually why the mapping class group is denoted by mod, because historically SL2Z was called the full modular group, where the word modular really is like a lot of places. And SL2Z shows up in a lot of places. But why is it cool that it's SL2Z? So not something I'm going to prove, but all the finite order elements of SL2Z have order 1, 2, 3, 4, or 6. And so before, when I had the hexagon, and you notice that when I sent one side to the other, right? So that was that order 6 element. And so we know that order 6 rotation in the mapping class group of the torus is going to map to the order 6 element of SL2Z. And moreover, it sort of makes sense that we would have an order 6 element in the mapping class group of the torus because there's a mapping class, because there's an order 6 element in SL2Z. So there should also be an order 4 element and then an order 3, 2, and 1, which you can just see by rotations of this hexagon. Okay, so that's cool. Now I can tell you what a Dehn twist is in like the last couple minutes. So Dehn twists are probably the most well understood elements in the mapping class group outside of like hyperelliptic involutions, which are so well understood in so many different contexts that it's like not even comparable. But okay, so the way we're going to define this is, so I'm going to formally, I'm going to like embed the annulus as just being S1 across the interval. So it is sort of like the cylinder, and I'm going to define a map T from A to itself, where I take T of theta of T, and this is going to be the point theta plus 2 pi T. Okay, so we're sort of like twisting it, right? That's all we're doing. We're just kind of twisting it. Don't try to picture this right away. It's very hard. We do pictures and maybe understand it. I don't really understand it anyway. But the special thing about this is that it fixes the boundary pointwise, which means that this is actually not just that it leaves the boundary invariant, but at each point on the boundary, it is the identity, which is what we want. And you can just see this by plugging in, right? Because it's either, because at 0, it's just not going to be a term at all. and at 1 it's going to be a full 2 pi term. So we're going to let S, right? S is going to be a surface, and alpha in S. So I'm going to draw my nice surface here. Doesn't matter how many holes it has. Whatever. It's going to have somebody say a number.
5.
5. Okay, cool. So let's draw 5 holes. Right? So let's just say this is S5, whatever. So we're going to let alpha be a simple closed curve. What does that mean? That means that it's a curve which the starting point is the same as the ending point, and it's simple, which means that it doesn't intersect itself anywhere else. So we can just sort of draw that by going around here and then coming back up. So I'll draw it in purple. That'll be cool, right? Boom. So now everybody can see it. Some other example might be what color would you say this is? Like magenta, maybe? I don't know. Definitely not fuchsia. So we're going to let alpha be a simple closed curve, and n is going to be a regular neighborhood around alpha. So what does that mean? It's going to be some neighborhood which kind of looks like a tube around alpha. And the point here is that you can pick some orientation preserving homeomorphism from the annulus to this neighborhood n around their simple closed curve, right? And so the Dehn twist about alpha is defined as this t sub alpha of x, and this is going to be phi composed with t, where t is over there, composed with phi inverse of x, if x is in this neighborhood, or is in this regular neighborhood, and it's just going to be identity outside of this regular neighborhood. So, sort of like, what is this twisting really doing? It's sort of just saying that in this neighborhood of the surface, we're just going to twist it around, or given by this phi and this alpha, right? So as we've constructed it, this Dehn twist depends on alpha and on the choice of homeomorphism phi. But what's really cool is that while the individual function depends on these parameters, first of all, you can show that it is a non-trivial element of the mapping class group. And as an element of the mapping class group, the isotopy class of this T alpha doesn't depend either on the choice of n or the choice of phi, right? So individual functions do, but its isotopy class doesn't. And what's even cooler is that now that we know the element itself doesn't depend really on this phi or this n, because this n you can sort of make it bigger, make it smaller. This phi you can choose to be like some weird homeomorphism. Maybe you have a wraparound a couple times instead of just once, or whatever it is. Moreover, you can show that this Dehn twist doesn't even depend on the curve alpha, but on its isotopy class. So this Dehn twist is really like a very well-defined element of the mapping class group up to isotopy. That's the, if you ever want to learn about mapping class groups, you will just see everything is up to isotopy. Everything. Sometimes it's only up to homotopy, but everything we're doing is up to isotopy. And this is great because we're dealing with like homeomorphisms. Everything really is very strict and very nice. Now, sort of, what does this thing even look like, right? To get an idea about what that looks like, we want to know what this looks like. So, this is one example of it, right? But I drew a cylinder here, right? So what does it look like on the cylinder? I'm using green this time. So this line over here, we can sort of just picture as a line this way. And it's going to map to a curve that sort of goes around this way, right? And so this is sort of the same, a little bit. Now, let's think about the torus, whatever.
Try to wrap it up a little.
Oh,
5 minutes.
I have 5 minutes?
Yeah.
Oh, that's cool. Okay, one concrete example is, so I told you before that you can realize this torus as sort of just folding up the square, right? So regardless of how large the square is, let's just say it has sides on the axes. Now, you can think about, let's say like this is 1, and this edge, this will just be like x, and let's say this is 1 over here, and this edge will be y. So we sort of have this curve over here, 0 to 1, and 0 to 1 over here, right? So these things, after I fold up my square to get a torus, these 0, 1, and 1, 0 curves in the plane over here determine curves that live on the torus. And what that means is that we can define Dehn twists about these two curves. And what's really cool is that the Dehn twist defined by these two curves actually generates the entire mapping class group. Which is also cool, and it tells us that this identification really does work because SL2Z is generated by 2 elements. Well, it's not, okay, I'm like leaving some stuff out. There's like some order 2 things, some order 3 thing. Don't worry about it, right? But I can tell you like exactly what these things are. So about the 1, 0 curve, the matrix you get is 1, negative 1, 0, 1. And about the 0, 1 curve, the matrix you get is 1, 0, 1, 1. Huge fact. For the mapping class group of any SG, so any surface with G holes and no punctures, it is always going to be generated by a finite number of Dehn twists, which like, big deal. Huge. Yeah.
Actually, no, wait till the end so you can finish.
Okay. Moreover, what you can show is that Dehn twists are actually infinite order elements of the mapping class group. And they are the simplest infinite order elements. The way you would show this is that if you take 2 curves on the surface, you can talk about their intersection number. So there's the geometric and the algebraic intersection number. They're both defined up to homotopy, so it doesn't really matter. But you can show that the intersection number grows with respect to, or grows with each iterate of the Dehn twist. And so you're never going to get anything trivial, because you're never going to get like back to the original orientation you had, because you're always going to have like more intersections. So you can never go back to this original intersection pattern of the 2 curves. And so this shows you that these things have infinite order. What's even cooler is that 2 mapping class groups, not only are they well defined, but mapping classes TA and TB are going to be equal if and only if A equals B, like up to isotopy. So the 2 curves have to be the same up to isotopy if the what's it called? If the Dehn twists are going to be the same. I guess nothing else I'm going to say is going to be that interesting. I don't really think I have like 2 minutes, right? So you can also say, like, you want to not only think about the mapping class group, or I'm sorry, about the Dehn twist, but also how does the Dehn twist change with respect to like applications of mapping classes? So if I have a surface S, right? Let's say a simple closed curve in S, which belongs to some isotopy class A, and I have a Dehn twist, again, which only depends on the isotopy class A, so I can just write TA, right? I don't need to write T alpha. So you want, and let's say I have some F in the mapping class group of S, and let's say this is represented by a function phi. So I want to see what does T of phi A actually look like, right? Because this is going to be some other isotopy class of a simple closed curve in S. And so as it turns out, this is actually really nice. This is equal to phi composed with TA composed with phi inverse. And with this fact and the other one where I said that the 2 Dehn twists are equal if and only if they're defined by the same isotopy class of curves, you can show some other thing, like you can show, or you can look at like when 2 Dehn twists commute, you can look at when the iterates of Dehn twists commute, and you can look at also explicit sets of, or explicit finite sets of generators for the mapping class group. And so these things, I didn't have enough time to talk about them as I wanted, but they really are like fundamental to the study of the mapping class group. And there is much more going on here than I have time for, but I think I'll stop here.
Let's thank Brandon.
by finitely many Dehn Twists, or is that just the subgroup?
Sorry, the mapping class group specifically of SG. So
Okay.
if you have like punctures, then the case is more complicated.
Uh-huh.
If you have boundary components, the case is more complicated.
But if just any mapping class can be decomposed into some composition of finitely many
Okay,
Dehn Twists.
so in this, there is a simpler case of, you can look at Mobius transformations of the upper half plane. Have you seen that before?
Mhm.
Okay, so you know they can be characterized as parabolic, elliptic, or hyperbolic,
Mhm.
right? This just depends on the trace of the element.
Yeah.
As an element of PSL2C, right? There's a similar classification for mapping class groups, which is called Thurston Classification. It's really hard, but the idea is that you can actually write every mapping class group. So it's either periodic, which means exactly what you think it means. It's just, it's literally periodic, or it's reducible, or it's something which, when you write it in purple, I don't know, okay, it's pseudo Anosov. So this is called the Thurston classification of mapping classes, and pseudo Anosov just, so you need to have a foliation on your surface, and so what this is telling you is that these mapping classes sort of stretch the foliation by lambda in one direction, say like horizontally, and it'll stretch by lambda inverse vertically. For the torus, you actually get like a lot. Like the pseudo-Anosov thing is really something more called like an Anosov package, and you immediately get like some more structure on it. But there is a decomposition for mapping classes of an arbitrary mapping class group. Finding sets of generators is harder. Explicitly writing anything down is harder. But you do have a similar classification. And you do basically end up writing a lot of this just in terms of, just like as matrices. Especially for the torus, you can do like everything very concretely.
Are you aware of how this relates to a geometrization of three manifolds?
God, I wish.
I'll tell you a little bit about it after.
Sure. Well, I think it's got to be like something to do. I think it's still something with like the mapping torus.
Yes.
Because
Yeah.
because the mapping torus is somehow supposed to encode the information of like each of the 8 geometries, right?
Yeah.
Yeah.
Well, not every geometrized manifold is a mapping torus, but like a huge number of them are.
Yeah. So I don't know any details. I just I didn't actually read that part.
I'll tell you a bit about
part
it.
of the part, but
Yeah.
anything else?
No more questions? Thanks.
No one leave yet because we have to take attendance.